Alrighty, good morning, my students. I just wanted to have a short lecture over the next topic. So the next topic we are going to be covering are chemical kinetics, or is chemical kinetics. Okay, the first thing that I wanted to talk about are the factors that affect the rate of your reaction. So the first thing I want to mention is that word rate. So by definition, a rate is something that's covered per unit of time. So that's what the kinetics of a chemical reaction are looking at. So the formal definition of kinetics is the rate at which an amount of reactants is converted to products per unit of time. So again, this is over a specific amount of time. So one thing I want to mention is for chemical kinetics, we are not so much looking at whether a reaction will take place or anything like that. We are just looking at the rate. How fast or how slow are my reactants being converted to products? Okay, so this is all about the time here. Okay, so for this lecture, I'm going to try to chunk the information a little bit better. So for this lecture, I'm going to be talking about 5 factors that will affect your reaction rates. So I already wrote out all the notes beforehand just to save some time. Okay, so the first factor that will affect your reaction rate is the surface area or particle size. Okay, so having a larger surface area will increase the number of particles that are available to collide. So looking at the collision theory, so all of this is going to be going back to something called the collision theory. Okay, so I'll just put a little asterisk here. So looking at the collision theory says that the particles in a reaction need to collide in order for their reaction to take place. That's a very simplified version of it, but that's what we're going to be looking at. They need to collide with enough force and in the correct orientation for that chemical reaction to proceed. So one of the ways to increase those number of collisions is by having a larger surface area. So one of the ways we can visualize this, and then I'll go through another example later, is if we look at 2 cubes. Okay, so I have cube 1, which is considered my large cube, and its measurements are 10 by 10 by 10. Okay, so that could be 10 centimeters, 10 meters, 10 nanometers, whatever arbitrary unit you want to give. So if I look at the volume and the surface area for this large cube, volume is your length times width times height, right? So in this case, it's going to be 10 times 10 times 10, or 10 cubed, which is equal to 1,000. So then next, if I want to calculate the surface area of a cube, it is 6a squared, where a is the length of one side. So then it's going to be 6 times 10 squared, which is equal to 600. So then if I were to increase this surface area, or affect the particle size, and I were to decrease the particle size to cube 2, okay, so for this cube, my length times width times height has been decreased to 1. So it's going to be like 10 times smaller. Okay, so then my volume is going to be the same thing, length times width times height, 1 times 1 times 1, which is equal to 1. In this case, my surface area, again, 6a squared, 6 times 1 squared, which is equal to 6. Now, if I wanted to match the volume of these 2 cubes, since cube 2 has a volume of 1, and cube 1 has a volume of 1,000, if I were to get 1,000 small cubes, okay, so if I have this times 1,000, right, to match the volume, so if I also multiply my surface area times 1,000, again to match the volume, I would have a surface area of 6,000. Okay, so that surface area is 10 times higher, 10 times greater than the large cube. So having that increased surface area means that these smaller particles are going to have a much larger number of collisions, and having more collisions happen per unit of time means you are going to have a much higher rate of reaction. So decreasing that particle size, increasing that surface area is going to be the first factor that increases or affects your reaction rates. Okay, so let's go to the next couple. Okay, so the next factor is going to be your concentration. So if there is an increase in concentration, more reactant particles are available to collide. Okay, more collisions will increase your reaction rates. Okay, so again, I just drew two beakers here. My drawings are not the greatest, or not the best. But let's say in this first beaker, I have a concentration of 0.1 molar. I increase it, and my concentration increases to 1 molar. So this one here is a lot higher, right? This concentration is a lot higher. So by definition, I'm going to have more moles per liter in this one, in my second one, than I am going to have in my first one. Okay, my first container, 0.1 molar, second container, 1 molar. So since I'm having a lot more moles, a lot more particles per liter here, I'm going to have a lot more possibilities for collision. That's why I was trying to draw these little arrows on all of them, showing that the movement of them means they're most likely going to be colliding a lot more. That increase in collisions means your reaction rate is going to increase. Okay, so let's go to the next factor. The next factor that affects your reaction rate is temperature. Okay, so an increase in your temperature causes an increase in your kinetic energy, or energy of movements. So if the particles have more energy for movement, or more kinetic energy, they will be colliding more often. So just remember throughout all of this, if you have more collisions happening, that means you're going to have a higher rate of reaction, or a faster rate of the reaction. Okay, so temperature, an increase in temperature will increase the kinetic energy. Those particles are going to be moving a lot more, which increases your collisions, which will increase your rate of reaction. Okay, so much faster already having the notes written down. Okay, the next one is your pressure. So this is mostly dealing with gases. Okay, mostly dealing with gases. And if we want to look or think back to our gas laws, right? If we want to think back to our gas laws, we'll be thinking about our Boyle's law, which says that pressure and volume are inversely related. Okay? Oh my goodness, sorry guys. So increasing pressure of a reaction involving gases forces their gases closer together, and this increases their frequency of collisions. Okay, so here we're keeping, losing my train of thought, I'm getting these notifications. So if we're keeping our volume constant, and we're increasing our pressure, okay, so that means our gas particles are going to have a lot less room to be running around in, right? So in my first beaker, let's just give this an arbitrary number and say that the volume here is equal to 1 liter, and my pressure right now is 1 atmosphere. Okay, so then the volume is going to stay the same. Volume is 1 liter here. My pressure is going to increase though. So instead of 1 atmosphere, I'm increasing the pressure, which I drew by kind of like forcing those particles closer together. So I'm increasing the pressure because now the particles only have that little area to move around in. So again, let's give this an arbitrary number of having a pressure, of 5 atmospheres. So since the pressure is so much higher, those gas particles are going to be colliding a lot more frequently. Okay, so there's going to be a higher chance of those gas particles hitting each other, running into each other, colliding. So that is a way to increase your rate of reaction. Okay, and the last way to affect your rate of reaction is by the addition of a catalyst. So a catalyst is typically a type of enzyme or protein that can be added to, well, that's in your body typically. A protein or an enzyme that's added to a reaction to kind of speed it up a little bit. So the way it speeds it up, and I have this graph, you might see this graph on the exam. So the way the catalyst works is it decreases your activation energy. So first, what is activation energy? So activation energy, I have the direct definition here in front of me. So I'm so sorry, students. Just mute that for you. Okay, so your activation energy is the minimum quantity of energy which the reacting species must possess in order to undergo a specified reaction. So in other words, it's the amount of energy that is needed by your reactants in order for that chemical reaction to proceed. So you might see a graph that looks like this, where you have your reactants and your products. On the y-axis, you have your energy. On the x-axis, you have a reaction coordinate. So this shows you the, excuse me, I'll try that. What word am I looking for? I don't know, I had a brain fart. But it shows you the passing of time, I guess you will, going from your reactants to your products. Okay, so then the purple line here, that purple line is showing you how much activation energy is needed without a catalyst. And then your green line is showing how much energy is needed once you have a catalyst added. So you can see this green line is a lot smaller, a lot shorter than your purple line. You can see the difference here is pretty great. So that difference shows you that by adding a catalyst, your activation energy is going to decrease. So your rate is going to increase. Okay, that reaction will be able to proceed at a faster or higher rate since your activation energy has been lowered. Okay, so those are the 5 ways that you can affect the rate of reaction, right? So we have the surface areas, number 1, concentration, temperature, number 2, 3, number 4 is pressure, and number 5 is the addition of a catalyst. Okay, so let's go over a couple examples. Okay, so let's see. Example 1, I didn't number these. It says zinc metal will react more vigorously to produce hydrogen gas in 6 molar HCl than it will in 1 molar HCl. Explain this observation. Okay, so first let's see, what are we looking at here? What information has been given to us? So the first thing I notice is the addition, or not the addition, excuse me, is the difference in concentration. Okay, so it says I have 6 molar HCl, and that zinc metal is reacting a lot more vigorously there versus the 1 molar HCl. So what's that difference there, students? Well, this 6 molar is a much higher concentration, right? So 6 molar HCl, that 6 molar HCl has a much higher concentration than that 1 molar HCl. Okay, so the brackets mean concentration, so whatever you write in the brackets. So if you were to see that on the exam, you see those brackets and HCl inside, you would read that as a concentration or the molarity of HCl. So having a 6 molar HCl, hydrochloric acid, is going to have a lot higher concentration than this 1 molar HCl. Okay, so why would that affect the reaction rate? Well, increasing the concentration of your HCl is also going to increase the amount of hydrogen ions that are available to react. Right, so you're going to have a lot more hydrogen, a lot more chlorine available to react. Okay, so having a lot more particles available to react with that zinc means you're going to have a much higher reaction rate. Okay, so let me just write that in for you. Okay, so increasing the concentration of HCl, right? Increasing the concentration of HCl increases the number of hydrogen ions available to react. So having more ions available to react with that zinc means you're going to have, a higher reaction rate. So that means the reactants are going to be converted to your products a lot faster in the higher concentration due to the availability or the amount of hydrogen ions that are present. Okay, so let's go to the second example. Example 2. It says, on a particulate level, explain why meat left out in the heat will spoil faster than meat placed in a freezer. Okay, so this is something that we all do, right? Whenever we go grocery shopping or anything, we put our meat in the freezer until we are ready to eat it, and we'll defrost it, cook it, etc., etc. Okay, so why is it that we don't leave meat out? Right, we know that it'll spoil, but why does it spoil so much faster? Okay, so the reason for that is due to, what number was it? Factor number 3, which is your temperature. Okay, so the meat left out in the heat is going to have a lot more kinetic energy than the particles of the meat that are placed in the freezer. Okay, so the particles in the heat or in the warm environment are naturally going to be moving a lot more quickly due to a higher amount of kinetic energy. So having more heat means higher kinetic energy. Okay, so the particles in the warm environment are moving more quickly, and therefore, since they're moving more quickly, you're going to increase the rate of collisions. Okay, so having more heat, more kinetic energy means more collisions are going to be occurring between the particles in the meat and the particles in the air. An increase in the number of collisions increases your reaction rates. So that's the reason why meat will spoil faster outside in the heat versus placed in the freezer. Okay, it has to do with your temperature. Having higher temperature, when the meat left out, the particles will be reacting a lot faster with the particles in the air. So those collisions are going to be happening a lot more frequently, which means that meat will spoil faster. Versus the meat placed in the freezer, the particles in the meat in the freezer are going to have a lot lower kinetic energy because the temperature is so much lower. So those collisions are going to be happening less, which means your reaction rate is going to be a lot lower, which is why meat stays fresher in your freezer, or anything will stay a little bit fresher longer when you place it in the freezer or place it in the cold in general. Okay, so let's go on to example number 3. Why does a solid log burn more slowly than a pile of wood chips with the same mass? Excuse me. Okay, so I'm going to draw here. Not very well, but I'm going to try. So let's say I have my solid log here. Right, this is my log. Okay. And I'm going to be burning this log. Say this log has a mass of, let's say 100 grams. Okay, so I'm burning that log. So why is it that this log is going to burn slower than if I have tiny wood chips that are also 100 grams? And say the fire is the same size, same heat, everything. My drawings are definitely not to scale, students, but hopefully you understand. Okay, so why is it that this one's 100 grams? They are both 100 grams, but the solid log is going to burn a lot more slowly than the wood chips. Okay, so this goes back to factor number 1, which is particle size or surface area. I'm sorry if my pen's loud. I'm trying to write quickly. Okay, so particle size, surface area. So the wood chips, right, this one here, are going to have a lot more surface exposed versus your log. So since they have a much higher surface area, so more particles are going to be available to react in the wood chips. So that's going to increase your rate of reaction. So more particles available to react will increase the rate of reaction. Okay, so that's the reason why your wood chips burn a lot faster than a solid wood log, because of the particle size or your surface area. So now necessarily just because these burn faster, your wood chips burn faster, maybe that's not what you're looking for, which is why people usually have a log in their fireplace. That way that fire can burn slowly over a period of time, right? So I live in Texas. I don't have a fireplace, but that's what I've seen. And that's what I assume, which is why they use logs versus wood chips in the fireplace. Wood chips will burn a lot faster, again, due to having that increase in surface area. The surface of those particles will are more available to react, which means you have, which means you will have a higher reaction rate. Okay. So that's it for this lecture, my students. I just wanted to go over those factors with you guys. A little bit later, either today or tomorrow. Well, today is Tuesday, right? April 7th. So at 3 o'clock today, I'm going to be hosting a Google Meet session. And in that session, I would like to continue going into the calculations for this unit, introduce how to calculate your reaction rates, all that good stuff. But I just wanted to introduce the concept with this first lecture, going over the kinetics and the factors that increase your reaction, or not increase necessarily, but will affect your reaction rates. Okay, well, I think that's it for this video, students. Have a wonderful